Good afternoon. Thank you for coming to this webinar on better use of hydrological data in flood analysis. I hope you enjoy it. It's something I'm very interested in and keen to show you the improvements we've made to our software to access the wealth of hydrological data that's now available to us. In this webinar, I'll first give you an overview of why it's important to use good quality data and maximize the amount of data you can bring into your analysis. I'll talk about sources of data, and this has improved dramatically over the last 5-10 years, particularly, well, in fact, even over the last year, there's been a massive increase in the quality and amount of data we've got ready access to. And we'll look how that new data can be used both in hydrological estimation, so improving the quality of our flood hydrology estimates, how big is a 1 in 100-year flood, the shape of hydrographs, and so on, as well as how it can be used to improve the performance of our hydraulic models. So once we've got our data into a model, how we can use this new data to further improve our models and give us greater confidence in what we're doing, and ultimately give us better confidence in the decisions we're making. At the end, hopefully we'll have time for a few questions. So why are we doing this? Incorporating more data into our analysis can significantly improve the confidence of our work and give us better answers. So when we're doing hydrology, when we're doing hydraulic modeling, we're only as good as the input data we're using. And by using greater data, more local data we have greater confidence in, we can reduce the uncertainty in our analysis. And ultimately, our analysis, our flood maps, our design information is used to design things, to design flood walls, to design flood defense schemes, to provide flood alerts to communities. And we want to have as much confidence as possible in these outcomes. It is important to recognize that there will always be inherent uncertainties in our input data, no matter how good the data is, how much data we put into our models, there will always be uncertainties. And it's important to recognize those uncertainties so we can assess the residual uncertainty in our work. And we've talked in previous webinars a lot about residual uncertainty analysis and why that's important. It's worth looking back on where we were and where we've got to. So I've been in the industry for pushing 20 years now, and the availability of flood data has improved immeasurably. When I first started working in the early 2000s, a lot of the data came on a single CD-ROM, so that was the FEH CD-ROM in the UK, which had catchment descriptors on it. Hydrological data was published in books, which were sent out every year, so the hydrological data yearbooks, and obviously they could be several months out of date, or over a year out of date very quickly, depending on what happened, and they only gave you summary information. If you wanted detailed information, if you wanted sort of instantaneous 50-minute level or flow data, you had to request that directly from the gauging authorities, and that could add weeks, if not months, onto the time it took to get hold of the data. That is now largely available for free across large areas of the globe. We can get this data pretty much instantaneously. It's regularly updated and it's really easy to access. So a big change has been the way in which we access this data. So an example is the Environment Agency's Hydrological Explorer tool, which has given us practitioners free access to all open stations in the Environment Agency's data set, and that can be accessed either through a website or through, importantly, an API. So that's a tool that lets software talk to websites or data sets, and that's what we've implemented in Flood Modeler, and I'll show you how that works later. So the more data we can use, the better quality data we can use, the better the decisions we can make, and really the barriers to accessing that data have fallen away immeasurably over the last couple of years. I'm going to have a look at how that data can be used both in hydrology and hydraulic modeling. I'm going to use some demonstrations as I go through this and drop into Flood Modeler as well to show you how this is being done. Starting off with hydrology. I've focused here on the UK, but this is equally applicable globally, where far more data sets are available to us. But in the UK, the primary sources of hydrological data are the National River Flow Archive, published by UKCH, and that's a great source of information about river gauges across the whole of the UK, including the peak flow data. This is the highest quality river flow data we've got. as well as quality flags and other information. And that for a long time has been accessible via our website, but is now also accessible by an API. So you can connect directly into that. So you can connect Flood Modeler to that. You can connect things like Python or R, so you can create your own codes and scripts and analysis. And that's a very powerful resource. There's also the FEH web service. That is still a website-based tool, which gives you access to catchment descriptors. How big is my catchment? How steep? How permeable? And that's a key source of data to go in our analysis, which I'll touch on in a moment. The big new ones are the hydrometric data available from the likes of Environment Agency, SEPA, NRW. The EA published the Hydrological Explorer a few months ago, and that has increased orders of magnitude the amount of data available to us. So every open gauge in England is available, where you can get hold of river flow, river level, rainfall data at different resolutions instantaneously. Only a few months ago, if you wanted some of this data, you'd have to send in data access requests and wait weeks for that data to come back. It's now available directly on the website or directly in Flood Modeler. And I say SEPA and other measurement authorities are also making their data available through similar tools. It's also worth touching on citizen science data as well, so mass collected data. I've put a link down there to the Met Office weather observation website, the WOW site, where you can aggregate data from personal weather stations. This is undoubtedly lower quality data. It's not QA'd in any way, and the instrumentation isn't as high quality as the likes of SEPA or the Environment Agency deploy, but the density is very high. So you've got a greater density of data of a lower quality. But that's been very useful for dealing with, say, summer convective events, where you've got huge differences in rainfall intensities, within a kilometre of each other. So some of the really high gauge points are often missing the intense storms, and you can use things like Weather WOW or Weather Wonderground to access local data and use that in your analysis, but being cautious, as I said in the earlier slide, about the quality of that input data. So how do we use this data in hydrological analysis? Well, our hydrology provides our boundary conditions for our hydraulic models. So when we're running the 1 in 100-year events, the 1 in 1,000-year event, that flow data that's going into that model has come from our hydrology. And if we don't get that right, then our results will be wrong. Globally, there are two broad methods for undertaking hydrology. There's statistical analysis of observed data. This is when we take gauge data, which I'll show you in a minute, undertake statistical analysis and use that to estimate the rarity of both historic events and estimate what future more extreme events could look like. So we're saying that was a 1 in 50-year event, and this is potentially what a 100-year event will look like. The other approach is conceptual hydrological modelling. This is when we divide the water cycle up into components, and we try and estimate what each component is doing in order to produce an estimate of flow. So there's an example on the right-hand side of the RFH hydrological model, where you're inputting rainfall and base flow conditions, and there's a model there that will give you a total flow out, a hydrograph estimate. And there are lots of these models around the world, and they all use different approaches to dealing with each of these components. But irrespective of which model you're using, the longer records, the higher quality flow records you can use really improve the confidence you have in this data. So for instance, with the statistical analysis, the longer duration record you've got, the greater confidence you've got in your extreme flow estimates. So if you've got 50 years worth of data, you've got relatively little confidence even in your sort of 1 in 50-year event. Or if you've got 400 years worth of data, then you've got a lot more confidence in your extreme events. The long-term data also lets us calibrate conceptual models. So you can take observed data, you can put it into your conceptual model and see how well it performs using observed rainfall and comparing that to observed flow. So really, the more data you've got, the more confidence you'll have. There are still some barriers to this. So I've said there's lots of sources of information. So the data is hosted on multiple sites in multiple locations. The data is often in inconsistent formats. So each supplier will use a different format. So there's often a degree of pre-processing required before that data can be brought into your analysis. So you often have to do some sort of transformation of the data before you can bring it into your hydrological analysis or into your hydraulic modeling. And what I'm going to show you next is some functionality within Flood Modeler version 7, which is due to be released in a few weeks' time, which is Hydrology Plus, which allows us to overcome some of those barriers and really make access that data a lot slicker. So if I just jump into Flood Modeler, this is the current version 7, which they will be released in a few weeks' time. And what I've done is brought in a simple river model of the River Severn, just down here. And I'm going to have a look at the gauge data, the river flow data available in this area. What I can do under the Hydrology Plus tab is I can switch on all the gauging stations in the UK. So there they are. That's every single gauging station in the UK brought in via these APIs. I'll just switch that off a second and zoom back into where I was. And I can inspect and interact with that data. So I'm just going to switch the flow data back on. There we go. So I only want to see flow stations. I'm going to ignore level stations. I just want to see flow stations. So I want to do some hydrology. And I can see lots of different flow stations in this area. And I want to understand the data a bit more. So let's take this one here right in the middle of my catchment area. Let's have a look at that one. So I can click on that. I can see there's flow and level data available here, and I can bring up the full record, which pops up as a separate tab. And this is bringing data in from the National River Flow Archive and the Environment Agency's peak flow data set live into Flood Modeler. I've got a load of information about this gauge, but in summary, there are some challenges with it. It's not very good at a very high flow, so it's good at in-bank flow measurement, but out of bank, it's not recording the flows very well, and that's recorded in the description information here. And also, it's not suitable for use in hydrological analysis, in peak flow hydrological analysis. But it does have a lot of gauge data. So if I click on the observed, it takes a second to cache the data, so it's loading in the full record for that site, and it is visualizing that for me. So have a look at what that looks like. By default, it shows the last year of data, but if I click on all, it'll show me all the hydrological data available for that site going back to when it was opened in 1971. And I can start to look at this in more detail. So I can see they've got this peak here in 2007. I'm going to zoom in on that. So I'm going to just zoom in on that a bit and zoom in again. And when I get right into the data, rather than showing me average data, it's caching in 15-minute instantaneous data. There we go. So I can see the flows recorded at this site at 15-minute intervals all the way back in 2007. I can inspect this by running my cursor across it, see those peak flows, and I can also move around as well. So if I want to see what happened a week previously, I can just click the button and it'll move around and give me data from the previous week or go back and forwards. And this is being streamed in live from the APIs. I can also switch this to show me level data instead. So that was flow data. I can switch that to level, and I can see the observed water levels at this site. And I can export this data too. So there's a nice export button, which lets me export this data in a range of different formats, which I can then use in subsequent analysis. So I can export it as a boundary condition for my hydraulic model. I can import it as a sort of a vanilla CSV file for further analysis, or I can export it as a calibration file. And I'll be doing all this a bit later on to show you how that works. And the nice thing is when I export this information, it takes all the metadata with it as well. So when it was exported, where it came from, who did it. So it maintains data provenance. A big challenge we've had historically is when we bring data into models or hydrology, a lot of that provenance information is lost. And so we've now got a way of maintaining that. I'm just going to have a look around. So that site is a flow station, but it's not a peak flow station, so it's not the highest quality data. The nearest upstream peak flow station is all the way up here at Bewdley. And if I click on that one, I get slightly different information. So I can see here, this is a flow station. It's got peak flow, and it's good for pooling and QMed, so it's a far better station. And when I look at this one, as well as the observed data, I've also got the peak flow data available to me as well. So I can see the AMAX data along the top, the annual maximum data along the top, and then I've got the POT data down the bottom as well. And again, I can export this and I can revisualize this as I'd like to. So that one's the upstream station. I've got the station in the middle of my study area, and then downstream I've got this next station at Hoare Bridge, which is the next peak flow station. And again, I can bring that in and I can see all the peak flow data available there. There's that big 2007 event I'd identified previously, and I can bring in the observed data as well. So what this tool's allowed me to do is have a sort of a catchment appreciation, so I can see where all the data is available. I can start to inspect it straight out of the box. I don't need to do a data request or go to different websites. I can do it all here where it's relevant to my model and start to understand it a bit better. And I've used this data to create an example of the hydrology. So the first thing I've done is I've pulled in that data from those three stations, Bewdley, Saxon Load and Hoare Bridge. And I can look at the maximum flow data, each of those from the 1970s through to today. And as you'd expect, the upstream data flows are slightly lower than those at Saxon Load, which got a bigger contributing catchment. And then those down at Hoare Bridge are slightly higher again, because they're further downstream, there's a bigger catchment. So that gives me some confidence that there's spatial consistency of the data. But when it comes to my flow estimates, this is really where we can demonstrate the importance of using local data. If I look at my 1 in 2 year event, my QMed event, and calculate it using a statistical method, there are numerous different ways of doing that. But if I'd taken the default approach, this catchment descriptors only approach, I'd get a peak flow estimate of about 650 QMex, which is a lot of flow to come down the river, but it is the 7. If I start to bring in local data, so I take a donor transfer approach and start bringing in local data, that drops by 100 QMex. So I've got to reduce my peak flow estimate by 100 QMex down to about 550. And if I use that local data at Saxon Load, if I've got sufficient confidence and trust in it, it drops the peak flow estimate even further down to 400 QMex. So this is my 1 in 2 year flood estimate, and you can see the range you've got here. And if I didn't have this local data, then the chances are I'd be using a very high level, which is likely to be wrong, likely to be an overestimate of the peak flow. What does that mean for bigger events? So we're usually interested not in the 2 year event, but the 1 in 100 year event or the 1 in 1,000 year event. So if I look at a flood frequency curve, if I use that default data, I'm looking at a 1 in 100 year flood event estimate of over 1,200 cubic meters a second. If I use the local gauge data, that drops significantly. That's down to about 800 QMex. And if I use the local data transfer approach, it's somewhere in the middle. So you've got a little 1,100 QMex-ish for the 100-year estimate. And again, this just shows the variability in our peak flow estimates and how susceptible they are to including local data, and why it's important to include local data. Otherwise, we risk under or overestimating flows. And that matters. So that model I produced earlier, I ran that through with both my default flow estimate and my refined one. You can see here, sorry, I've got a village here, just the end of Station Lane, which has got a few hundred houses in it. And looking at the 100-year outline using the default hydrology, that whole village, despite the fact there's a flood defence there, is overwhelmed. It's all underwater during that event. Whereas if I put my refined hydrology through using the Saxon Load data, that flood extent contracts quite significantly, and it's kept on the wet side of the flood defence. You can see this shape here as to where the flood defence is, and that's suggesting that there is less risk to that village. And this shows how important this is. Just adding an extra station into my analysis has changed the flood extents dramatically. I'm not saying that the Saxon Load data is correct. There's obviously quality issues with it, but it demonstrates how much that can change the flow estimates. Just moving on to hydraulic models. So I showed you how we can use hydraulic modeling, hydrology data to improve our hydrological estimates. When it comes to hydraulic modeling, it's equally the case. We need to improve our confidence in our models. In addition to the gauge data, we may also want to bring in things like observed flood outlines, which are also available online, rack mark data, which are observed flood levels during an event, the river gauge data, and importantly, flood mechanism data, observed flooding information. So increasingly, we've got access to things like videos, images through social media, as well as flood reports and aerial photography. So this is a This is an image from the 2015 flood in Cumbria, and it very nicely shows how the flood defences are being overtopped and where they're being overtopped during this very extreme event. And this is really critical information when we come to calibrate and prove our models. Model proving is a critical part of any hydraulic modelling or flood study. And what this does is it reduces the uncertainty in our model results. So we're refining our model using observed data, and therefore we're narrowing the uncertainty in our model. It demonstrates performance, so it shows to our clients, to our colleagues, to the community at risk, how well the model is performing, and it gives them confidence we can use these models as tools to understand flood risk and design mitigations. But it equally helps us quantify uncertainty. I mentioned residual uncertainty earlier. It helps us quantify that uncertainty. So how do I prove my model? There are two things here. There's calibration and verification. Calibration, to my mind, is when we're running observed information, so observed flow, rainfall through our model, comparing it to the observed levels and mechanisms at our site, and then using that information to adjust the model, to tune the model, to change Manning's values, bridge structures, and so on, such that our model better represents what's on the ground. Whereas validation is when we do the same, we run that observed data through our model, but we're not making any further changes. We're using that validation information to extract model performance information. And you can imagine a site without any observed data, you're using default values everywhere, and you're highly likely to get issues with your results. So if you can calibrate your model, it will give you better results. Again, I'm going to jump into Flood Modeler and show you what that looks like with the new tools in Hydrology Plus. So if we go back to my site of interest at up to 1.7, I've got this gauge right in the middle here, and I want to use that in order to calibrate my hydraulic model. So what I've done is I've gone into that station. Let's reload the data. I'm interested in this 2007 event, so I'm zooming a bit on that. And it's going to drag in the 15-minute data for me, the higher resolution data. So I want to model this I want to put this flow down my hydraulic model, then compare how the model performs against the recorded data. So I'm going to export that data out as a flow time boundary, as a boundary to my model, click export and save that. I'm then going to go back in and export the level data. So that's rather than flow, I want the level data of that gauge. I'm going to export that as a calibration file, a cal file, and I can use both those bits of information to see how well my model's performing. This is a case of here's what I did earlier, because the model will take a little time to run. So that event file I exported is over here. So this July 2007 event, and I can have a look at that. Give it a second to load. There we are. So this is that data I was looking at on the gauge has been converted into a model input file, and you can see it's maintained all the date information as well. So it's and there's also a comment file in here as well, which gives me all the metadata. So it tells me where that data came from, when it was exported, which gauge, even who did it. So it's me who's extracted that information. I can use that in my hydraulic model. So if I open my 1D model file up, what I've done is I've simply dragged that event file into my hydraulic model and used that as an event in order to rerun my model. So it's replaced the boundary with that new data I've taken. And I can then run that hydraulic model. So that takes about an hour or two too. So I'm going to let you watch that. I ran this early this morning. And what I can do is I can look at the results at different locations. So if I look at this node here, right next to the gauging station, and plot a time series, I'm loading in both the results from my hydraulic model, this ZZL file at the top, but also the calibration data as well, so that cal file I exported earlier. If I plot that, I'm seeing both the blue is the modeled results, that's what the hydraulic model estimated the peak flow would be past that site, and the green are the calibration results. So these are the observed data, so I can see how well the model's done. And for a first pass, it's done very well. So the timings are about right. The hydrograph shape is about right. It's missed a peak. So if I zoom in a bit, The peak from the gauge was 11.42 meters, whereas my model is about 100 mil lower than that. So it's not perfect, but it's not a bad estimate. And what I can do now is start to adjust my model to better fit that. So change the schematization, change the parameterization to improve how well my hydraulic model is doing. And this previously, without Hydrology Plus, would have taken hours to do, because getting the data and formatting it and bringing it all in, I can now do all the setup and the analysis in literally a few minutes. So just going back to my presentation to close out. Hopefully what I've demonstrated over the last half an hour is there's a real rich source of hydrological data available to us now, and it's changed massively since I started work in this field. And that tools such as Flood Modeler with Hydrology Plus give us easy access to this data, so really we can get hold of the data in seconds. I've demonstrated how the use of that data can improve our hydrological estimates and our hydraulic modelling, giving us better outputs, and significantly reduce the uncertainty within our hydraulic models, and show how important it is to use that local data and be aware of that local data.